Welcome to lecture 2. So in this lecture we'll talk about ethers and epoxides and thiols and sulfides. So this is a combined chapter that includes two separate types of compounds. So we'll go along with it and you'll understand it much better as we move along in the chapter. So in this lecture we'll try to discuss introduction of ethers, the nomenclature of ethers, the structure and properties of ethers, crown ethers, preparation of ethers, and reactions of ethers. And we'll see how to nomenclature of epoxides, the preparation of epoxides, and enantiomer selective epoxidation. And we'll talk about ring opening, and we'll finally complete it with thiols and sulfide, and we'll see the synthesis strategies that involve epoxides. So with that, let's start the introduction of ethers. So what is an ether? So an ether is basically a group. So it's an ether group is basically something that contains an oxygen atom that is bonded to two alkyl groups. So R, O, R dash is an example of an ether. So dash R groups are generally alkyl, can be alkyl, aryl, vinyl, right? But cannot be acyl groups. So the only chance is they cannot be an acyl group. For example, if you consider the idea here, and you consider two oxygens in the adjacent carbons, they are connected to the adjacent carbons, then this becomes an ester and not an ether. So that's the reason why we don't use acyl groups. So where do we use ethers? So ethers are generally a common functional group. So they're generally present in many natural and synthetic compounds. For example, vitamin E is an antioxidant that uses an ether group in it, and fluoxetine is an powerful antidepressant that's commonly known as Prozac. So that also contains an ether group. So morphine is another opiate analgesic that generally used to treat severe pain. So here also you find the ether group. So how do you name ethers? So naming ethers, the common names are generally used for ether. So the first thing we do is we name the each R group that is present inside the compound, and we arrange them alphabetically, and we end it with the word ether. For example, if you have a chemical structure that says, let's say, so let's say this is an example of a compound. So in this example here, notice that the side chains are the ones that are important. So there is two carbons here, and there are two carbons here. So this side is an ethyl group, and this side is an ethyl group. So both are ethyl groups, so we write it's a diethyl ether. For example, if you did not have two ether groups, for example, let's say you had this structure. So in this structure, notice that there are three carbons. So 1, 2, 3. So these three make it a propyl group, and this is a one carbon compound. So there is a methyl group. So we arrange them on the name of their alphabetical order. So if you take the alphabetical order, methyl comes first before propyl. So we write methyl, propyl, and then we end up with the word ether. So whatever is a side compound, write it as that yl. So as an alkyl, so that alkyl is what represents the final structure. So now let's discuss how do you name ethers in the IUPAC nomenclature. So in the IUPAC nomenclature, the larger R group is the parent chain, and the smaller R group is called as the alkoxy substituent. So whenever we write this structure, we write it as an alkoxy group. So what does that mean? If you take a general structure of ether, so whichever is the parent group, parent chain, the longer one, so the larger carbon chain will become the parent, and the one that is left out becomes the alkoxy substituent. For example, if you see the compound here, the largest structure is pentane, and there is an ethyl group. So ethyl, but there is an oxygen attached, so it becomes an ethoxy group. So the final compound is ethoxypentane. But this brings back the question of what is the structure and what are the properties of ethers. So the bond angle in ethers is generally very similar to that we find in water and in alcohols. So the oxygen here is sp3 hybridized. The reason it's sp3 hybridized is because it does not have a double bond. So it does not have a double bond. If it has a double bond, then it would have been sp2 hybridized. So oxygen with a double bond would have been sp2 hybridized, because oxygen here is connected to two separate compounds. So this becomes sp3 hybridized. So this sp3 hybridization leads to the larger R group, which has the wider bond angle. So whichever is the larger R group, so that gives you the wider bond angle. So for example, if you take the example of water, if you remember sp3 hybridization, the general angle is 105. But if one of the groups is methyl, it becomes a larger and larger, so that increases the angle to 109. And dimethyl ether increases the angle to 112. So the larger the R group, the wider the bond angle. So we already know that, if you recall, alcohols have a relatively high boiling point because of the presence of hydrogen bonding. So this hydrogen bonding here is the bonding between the lone pair of electrons on a highly electronegative atom, and the hydrogen bonded to a highly electronegative atom. So here this is the electron and this is the hydrogen that's bonded to an electronegative atom. So ethers in general can act only as hydrogen bond acceptors. So they can accept hydrogen bonds because of the presence of the chance that they do not have themselves have a proton. So because of the lack of that proton, they cannot directly have a general structure, or they cannot form their own bonds, but they can act as hydrogen bond acceptors to other compounds that can act as bonds. For example, when you mix an alcohol in an ether, they still do form a hydrogen bond. Now, so ethers cannot hydrogen bond among themselves, so the general boiling points are much lower than alcohols of comparable size. For example, ethanol has a general boiling point of 78. Because of the lack of hydrogen bond, dimethyl ether has negative 25 and propane has negative 42. So notice that the more the lack, so presence of oxygen does make an effect on the boiling point, because it does make it a little more electronegative. So there is a chance of having a lot more attraction in terms of their consequence. Now, the larger the ether, the higher the boiling point. So the more larger the ether, the higher the boiling point. This is due to the forces that we talked about, which is the London dispersion forces. So the more the number of carbons on the outer structure, that carbons cause itself to create a London dispersion force or temporary dipoles. So it creates temporary transient dipoles. So this temporary transient dipoles cause the forces to increase between them because of a larger surface area. So the larger the surface area, the higher the force. So the force will increase. Now, let's look at the next part. Ethers in general are generally used as common solvents, specifically for organic reactions. For example, the more common ones that you will see is diethyl ether, tetrahydrofuran, and 1,4-dioxane. So the relatively low boiling points, these are due to the easily moved by evaporation. So they are generally fairly unreactive. This is one of the reasons why they can do that. So let's discuss the next one, crown ethers. So crown ethers are basically metal atoms with full or partial positive charges are generally stabilized by ether solvents. Why is that the case? If you look at a general compound and mix it with magnesium, what happens when you mix it in an ether is that the oxygen having a partial negative charge gets attracted to the partial positive charge of the magnesium. This what it does is it stabilizes the magnesium atom. So it does not move the magnesium atom up or down. So it stabilizes the magnesium atom to stay in place. So the compound that you see right now is the ethers are generally the ones that are used as solvents in Grignard reactions because they can stabilize the magnesium atom. So crown ethers are generally shown to have formed specially really small strong attractions to metal atoms. For example, 12 crown 4, 15 crown 5 and 18 crown 6. So here the first number represents the number of carbons, and the fourth number, the last number represents the number of oxygens. So again, carbon, oxygen, carbon, oxygen. So the multiple other groups that result in, they are also result in strong metal attractions. So their numbers in their names refer to the total number of atoms and total number of oxygens. Now let's take a look at the example here. So the size of the metal ion must match the size of the crown to form a strong attraction. For example, a compound 18 crown 6 only is the ideal size to trap the magnesium potassium cation, because this space can only be filled by a potassium cation. So because it's the appropriate size and it's easy to get itself attracted to there, because it concentrates a lot of negative charge. Notice that the internal is a lot of partial negative charge. So which means that any atom with a positive charge can easily get attracted to the a lot of negative charge being put in one place. So crown metal ions in general are not soluble in low polarity solvents. So the crown ether complexes to the metal cation, so they result in the complex. The resulting complex is going to be soluble. So crown ethers in general are used to help ionic salts needed for organic reactions to dissolve in organic solvent. The reason is because polar compounds do not dissolve in non-polar compounds. So to create that dissolvability, we use crown ethers as a source to dissolve ionic salts into organic reactions. So crown ethers in general, the other one is the fluoride ion. So it is readily to react with potassium, and that is hosted by 18 crown 6. So without the crown ether, the solubility of Kf in benzene is really minuscule. So adding that actual crown ether, enhances the reactivity of the compound. So it easily splits the compound and takes away the potassium. So it depends on the choosing a crown ether depends on the metal cation present in the reaction. So for example, 12 crown 4 generally solvates lithium, 15 crown 5 is used for sodium, and 18 crown 6 is generally used for potassium. Next, how do you prepare ethers? So the industrial way of preparing ethers is by using diethyl ether, is generally prepared by acid catalyzed dehydration of ethanol. So they are generally done by the acid catalyzed dehydration of ethanol. So understand that this acid catalyzed dehydration is the process of dehydrating an alcohol, dehydrating ethanol, which means that we are taking out H plus and OH minus from ethanol. So remember the idea that we are taking out H plus and OH minus. This is not hydration, this is dehydration. So the first thing that happens is the acid catalysis. So let's take a simple example of this structure. So let's take a look at this reaction. So there are three main processes that occur. So this process that we talk about is called the acid catalyzed dehydration. So there are mainly three processes that occur. The first is the proton transfer, the second is the SN2 attack, and the third is the proton attack. So the first thing that happens here is that the ethanol gets attacked by protons. So what will happen here is that it undergoes deprotonation. So the first thing is protonation. So what happens here? The oxygen attacks the proton. So the proton will give away its electrons to the oxygen and bond itself to the oxygen. So this results in this hydrogen bonding to the oxygen. Then the second part will be the SN2 attack, where another ethanol molecule will come and attack the carbon, the alpha carbon that's bonded to the oxygen. So when it attacks the alpha carbon, so what happens here is that this alpha carbon, when it bonds here, so it results in an oxygen with two methyl groups attached to it. So it basically bonds itself in that place. Now when it bonds itself, what happens here is that the two electrons that are there will go to the oxygen and leave out this structure. So let me show you how it looks like.
So the oxygen, hydrogen, hydrogen, so which has a positive charge. Now, with that being a positive charge, the positive charge itself has much more charge. So what it does is it would rather take its electrons away. So for it to take an electrons away, the problem is oxygen is not good living. So what it will do, what happen now is an OH group from another ethanol molecule. So the oxy-OH group here will come and attack the carbon. So when this attacks the carbon, what will happen here is that these two electrons are then donated to the oxygen. So the basic structure looks somewhat like this. So where the molecule so now this oxygen here also has two electrons with a hydrogen and the hydrogen. So notice that this here is what we call the transition state. Let me write it in a bracket so that you understand better. So this here is the transition state. What happens in the transition state now is these two electrons are donated to the oxygen, and the two carbons here will end up. So again, what will happen again here? The two oxygens here, the positive charge here, will be taken away when the bond here it takes its electrons away from hydrogen and gives it to itself. So this leads to the hydrogen going out as H plus, and this entire molecule going out as H2. So this then results in the final structure formation where you end up with the final structure of ethyl. This is how you generally get the final structure. Notice that there are two things happening here. One is the proton attack that happens here. So this is separately mentioned in this reaction here. So where another ethanol molecule attacks the proton. But we can simply write it as a single reaction where there is one protonation, that deprotonation that occurs, and one water molecule that's done. So because the water molecule is being removed, that's the reason why we call this a dehydration reaction. And why do we say acid catalyzed? Just because this reaction wouldn't start without an alcohol. So this reaction wouldn't start without an acid. So the H3O plus molecule. So to create that H3O plus molecule, you need an acid. That's the reason why this is a dehydration reaction. So this is the process of acid catalyzed dehydration. So let's look at the next way of synthesizing ethers. So what we call that the Williams-Hunt ether synthesis. So it's also a viable approach for many asymmetrical ethers. So whenever I say the term asymmetrical ethers, meaning that both sides are not the same. So whenever you have one side being the other, so for example R and R not the same. For example, one can be a methyl group, the other can be a propyl. So the method that we saw now is the process that's commonly used for alcohols where symmetric ethers. So this method is generally used for symmetric ethers, and it's only useful for specifically for diethyl ethers because it's efficient for diethyl ethers. So let's look at a process where we can create the ethers for asymmetric ethers. So this process is called Williamson ether synthesis. So the approach here is the process of the first happening, this is a proton transfer, and the second we do nucleophilic attack. So let's take a look at this reaction separately. Now, so look at this reaction here. So what is happening here? So the number one thing, so the number one first process is the process of proton transfer, and number two is nucleophilic attack. So in the number one process, there are two steps in this process where we use two different substances. In the first process, we use sodium hydride, which facilitates the proton transfer. So what happens in proton transfer? So the hydrate molecule that's created in NaH will attack the hydrogen and will result and form H2. So leaving the electrons to the oxygen. So where the electrons go back to the oxygen. So what happens here? R O H. So when it reacts with NaH, Na will generally react and form Na plus and H with 2 electrons minus. These 2 electrons will attack the proton, and these 2 electrons are then given away to the oxygen. So this creates the first oxide or alkoxide where the oxygen gets a negative charge. Once the oxygen gets a negative charge, there is also a sodium ion that's still there. So the sodium ion will stay its place. The next process, it will undergo the RX. For example, let's consider that you have a methyl CH3X. So the X here represents the halide. Notice that in the secondary reaction, the RX is an alkyl halide. So the RX here is an alkyl halide. So which means that we have to use an alkyl halide in this reaction. So let's take this example here. Let's consider that we are using a compound methyl halide. So methyl halide, you have 3 hydrogens and a halogen. The halogen in itself is really electronegative. So because it's highly electronegative and highly electrophile, so carbon makes it partially positive. So the halide will take its electrons and move out, resulting in the carbon. Where what will happen? Why is it going to do that? Is because the oxygen here, because of its negative charge, so the oxygen here, because of its negative charge, attacks the carbon. Then the carbon will donate its electrons to the halogen and bond with the oxygen. So this results in R bond O, double bond, 2 electrons, bond CH3. Plus, now the X here, which has taken out 8 electrons, will move out, and the Na and the X will combine together and form NaX. So the byproduct is salt. So if you use a methyl chloride, you get methyl sodium chloride. So this is how the reaction in general occurs. So there are two processes that are happening. Number one is the photon transfer, and the number two is the nucleophilic attack. The nucleophile here becomes the alkoxide ion. So notice that this alkoxides are really strong bases. So it's a really strong base, so it can undergo a nucleophilic attack. So most commonly the nucleophilic attack here is SN2 reaction. So that's one way of doing this reaction. Now, so we talked about the process of Williams ether synthesis because this is an SN2 substitution. So it only works well with unhindered alkyl halides, which means that it has to be either primary alkyl halides or methyl alkyl halides. So it does not work for secondary and tertiary. So it does not work for secondary and tertiary. So consider the two possible routes to synthesize methyl T-butyl ether via Williams ether synthesis. So there are two ways of creating a much more complex structure of ether, much more complex ether. For example, we can take turbidyl alcohol and undergo Williamson ether synthesis where we use sodium hydrate and methyl iodide, where we end up with the final methyl tributyl ether. So this route here, the second route here, is not going to work easy because when you use methyl alcohol and use NaH and a complex iodine, an alkyl halide, this is not going to work. The reason I mean is because this here has to be a simple halide, right? Provided it's generally a one primary or methyl, so it cannot have a tertiary halide. So this is the only route for you to create methyl, methyl trimethyl ether. Next, the other way of preparation is the process of oxymercuration and demercuration. If you remember from the topic of how to synthesize alcohols from alkenes. So if you remember from alcohols and alkenes, so the process undergoes this way where if you use mercury here, so oxymercuration and demercuration of this process, what we do here is we have two carbons. So there are two carbons here. So the two carbons are named based on the less substituted or more substituted, depending on the type of bond that is being connected. Notice that here it's connected to two big groups, but here there's only one hydrogen and one big group. So here you end up with a less substituted carbon here and a more substituted carbon. So in alkoxymercuration, the water divides into two parts. You have OH minus and H plus. The OH minus will always go to the OH group will always go towards more substituted compound, and H plus will always go to hydrogen will always go towards less substituted carbon. So this results in the formation of an alcohol, more commonly a secondary or a tertiary alcohol. So this here is based on Markovnikov-Regis electron. So Markovnikov understands that the heavier atom goes to the more substituted side, the lighter atom goes to the less substituted side. So in this alkoxymercuration and demercuration, can you use the same method to synthesize this? Yeah, you can, but in place of water, you will have to use alcohol. So the alcohol here does not split into R and OH, rather it splits into alkoxide, RO, and it splits into hydrogen. So the exact same reaction, but RO goes to the more substituted compound and the hydrogen goes to the less substituted compound. So the exact same reaction, in place of OH we have OR. So this results in ether formation. So also it uses the same Markovnikov we just did.
So let's discuss the reactions of ethers. So ethers generally can undergo what we call acid promoted cleavage. So the understanding here is that if you consider an ether ROR, it can split itself completely by acid promotion. So this process is called the acid promoted cleavage. So where does this R and R go? So the RR will go and form alkyl halides RX. The oxygen will mix with hydrogen and form H2. This here is the process of acid promoted cleavage. So let's look at the first reaction. So the first reaction is the formation of the first alkyl halide. So what happens in the first alkyl halide formation is the oxygen molecule undergoes proton transfer again. So the oxygen attacks the proton on the acid and gives away a halogen with its electrons. So this creates an ion called the oxonium ion. So this here is called as an example of an oxonium ion. So this is a positively charged oxygen with two side chains that are attached. Now it undergoes an SN2 reaction from the halogen that's released in the first reaction. The halogen attacks any one of the carbons on either side and results in the formation of an alcohol. So this here results in the byproduct is the alkyl halide CH3X. Now the second time what happens again, the same thing, the alcohol itself again undergoes the same reaction. It reacts with the proton and it cleaves it releases a halogen. The halogen then forms again, it creates an oxonium ion. The oxonium ion again then gets attacked by the halide ion, the carbon. So again it forms the alkyl halide. Finally it combines and forms H2. So let's take a look at this reaction closer. So let's take a simple ether. So the first thing that happens here is that if you take any acid, for example HX, so best example of this acids is hydrohalic acids. So the oxygen with its electrons will attack the proton. The proton, noticing that it's going to bond with the oxygen, it releases its electrons and gives it to the X here, the halogen. The halogen now takes 8 electrons and goes out. So results in the formation of an oxonium ion. So where CH3, oxygen with 2 electrons and a hydrogen with a positive charge. So oxonium, the oxygen with a positive charge here is generally called the oxonium ion. Remember that oxygen generally does not have a positive charge, it generally gets a negative charge. But this time you have an oxonium ion. This oxonium ion gets attacked by the X minus that's released before. The halogen, the halide ion. The halide ion only attacks the carbons
and when it attacks the carbons, it releases the, so notice that it already has the electrons, so it basically takes the 2 electrons and donates it back to the oxygen. So this results in the formation of CH3 bond X, right, plus, and it creates the formation of the alcohol, CH3 bond O with 2 pairs of hydrogen electrons and a hydrogen. So this is the first alkyl halide formation. So notice that this is the first alkyl halide. Let's look at this alcohol again. So let's use this alcohol in the reaction again. The exact same thing happens again if you react it with an acid. Again the oxygen attacks the proton, so the proton donates its electrons back to the halide. So again you end up with CH3 bond O bond H. So it has 2 hydrogens again with a positive charge. Again, anytime you have an oxygen with a positive charge, it's an oxonium ion. Now again it gets attacked by the halogen that's released. So the halogen attacks the carbon again. Why does it attack the carbon? The main reason is because that's the only easily accessible one, and that's the largest structure that it can easily pick out of the entire structure, because hydrogens are really small and it cannot bond with hydrogens easily, because oxygen has much more control over the hydrogens. Now the CH3 group again donates its electrons to the oxygen, so therefore resulting in the formation of CH3 bond X, again another alkyl halide, plus, notice that when it gives its electrons to itself, this is 2 hydrogens with an oxygen, so you end up with oxygen with 2 pairs of electrons and 2 hydrogens. Again this molecule is the water molecule. So this is the process of acid promoted cleavage. So this is the process of acid promoted cleavage. So the X can be any one of the compounds. So notice that it has to be a hydrohalic acid. So preferably the hydrohalic acid either has to be, the X has to be chlorine, bromine and iodine. The reason is because this is an SN2 reaction, and SN2 reactions only work with chlorine, bromine and iodine. It does not work that good with fluorine. So that's the reason why end up with hydrochloric, either HCl or HBr or HI. So that would be the best of the acids that can be used. Next, let's look at the next reaction, so which is the acidic cleavage of ethers to produce an alkyl halide. Generally works with HBr and HI. So the dash R group is tertiary, and the cleave in general occurs via SN1 mechanism. So if the R group is vinyl or aryl or vinyl, the substitution by reaction will not occur. So for example, if you take one of these alcohols, one of these complex compounds where one of them is an aryl compound, so the aryl compound will generally form a phenol and that's it. So there is no second time cleavage. So notice that this does not again undergo further alkyl halide formation. So it stops right there. So the only thing here is that for if it's an aryl or a vinyl compound where it has a double bond, so or if it has multiple, if it has a cyclic structure, double bonded cyclic structure, which does not undergo substitution reaction. Next, ethers also undergo what we call autooxidation. So the autooxidation is the process of adding oxygen to itself to create hydroperoxides. So this is a slow process, but ethers do have this process of undergoing through a free radical mechanism. So the laboratory samples of ether generally frequently tested for presence of hydroperoxides, because they are generally, before they are used, because they can be explosive. So let's take a look at this mechanism. So there are 3 steps in this reaction, in this radical reaction. The first step is hydrogen abstraction. So the second step is coupling, and the third step is hydrogen abstraction again. So let's take a look at this mechanism and let's go through it once again. So let's take a look at this reaction now. So let's start with there are 3 steps of any radical reaction. So the first step is initiation. So let's look at the step of initiation.
So here you have an ether. So this is the ether. So this ether now has two lone pairs of electrons. And notice that this is a carbon. The carbon also has a hydrogen. So what happens here is that the first step is initiation. So initiation basically means that there is an initiator radical. So there can be any radical with single electron that initiates the reaction. So this initiator now, what will happen here is that the hydrogen splits its two electrons. Notice that there are two electrons here. These are the two electrons. One of those electrons will go to the carbon and the other electron will go towards the hydrogen. So, and the initiator, what will happen? This will come with one electron and the hydrogen goes with one electron and forms a separate substance. This results in the initiator where you end up with the ether having a single electron on its carbon and the oxygen having its two lone pairs. Now, once the initiation occurs, so the second step in any general process is the process of propagation. So the second step in a radical mechanism is the process of propagation. Remember that we talked about auto-oxidation, meaning that the propagation occurs due to oxygen. Now let's take a look at oxygen in itself. So here we have, let me copy the structure. So you have the structure here. This, when mixed with oxygen, remember that oxygen in general has a double bond, but the oxygen inside has two lone pair of electrons each. So what will happen here, this oxygen will split into two parts. It also initiates the radicalization. So this results in the formation of oxygen monobond. So with two electrons on each side. So these are the two electrons that are from here. So these are the two electrons. Now once these two electrons come out, what will happen? So the process of coupling starts. So the coupling process is basically taking into consideration the idea that so here this comes in and this comes in and forms a bond. So what will happen now? So this final product. So this bonds to an oxygen and that also bonds to an oxygen. So you'll end up with a complex compound. Now this complex compound, this is satisfied because these are the two electrons. Notice that, let me write it in blue. So this is the electron here and this is the electron here. So these two are the electrons that come and bond here. Now once they bond, there is another oxygen with one more oxygen left, one more electron left. So that also has to be satisfied. So for that to be satisfied, what will happen now is this compound then undergoes another process. So where it undergoes hydrogen abstraction. So remember the initiator. This here is the initiator. Notice that this is the one that has one single electron left. So that one single electron will basically start the initiation process again back. So let me write it again. So this, when mixed with another ether, so remember the hydrogen there on the top. So in the first compound that we talked about. So notice that this here is the initiator which starts the reaction. So where it takes its own electron and it donates its electron back to oxygen. So this here again creates the compound. So let's look at the final compound that it creates. So the final compound that you end up with is
bond H. So look at this structure. Here you have an oxygen on one side, and the carbon has one oxygen on one side and an OOH group on the other side. So whenever you see bond OOH, remember that this is a peroxy group. Especially because it's an OOH, it's a peroxy acid group. So because this is a peroxy group, so it becomes a peroxy acid group. So this here is the second process. So to terminate the reaction, so what will terminate the entire reaction here? Notice that along with the product that you have, you end up with the R radical from the ether. So these radicals will combine together. So what will happen? These two radicals will combine together and create a complex structure. So that complex structure will look somewhat like this. So this complex structure. So this process, the final process of termination, is called as coupling. This is the process of termination. So this process is called auto-oxidation. The reason auto-oxidation is dangerous is because peroxide is an explosive compound. So this compound is an explosive compound. The reason it's explosive is because it's unstable. It's an unstable and an explosive compound. This is one of the reasons why this reaction in general occurs. So to summarize this reaction, we can write it as RH plus O2 gives ROH. So this is the net reaction of what is happening inside the structure. So the reaction is slow, but all the old bottles of ether will generally invariably contain a small concentration of this hydroperoxides. So which makes the solvent very dangerous to use. So because they decompose violently when you heat them, so many elaborate explosions will be caused by distillation of ethers, so that were contaminated with hydroperoxides. So the ethers that are generally used in laboratory, so they have to be tested for the presence of hydroperoxides, and they will have to be purified prior to their use. So that's the reason why never use an ether directly, because they can have some amount of hydroperoxides, which can be really dangerous.